the those kind of key metrics that we're going to use to constrain the behavior of our model. And we're also going to have some kind of uncertainty on the emulated outputs because our emulator isn't perfect, and we want to know how much error we might expect from the emulation. And the way that we are doing this here is via an ensemble of neural networks. So these, everything I'll show today is just simple kind of feed-forward neural networks, but we can consider different kind of styles moving forward. And so basically what happens is we pass a set of parameters into an ensemble of n neural networks. So here I'll present results showing 100 neural networks. Each of those neural networks will generate outputs, and then we will consider our emulated output the mean of all of these different outputs, and the uncertainty of that emulated output from the standard deviation of these outputs. And we can kind of see significant benefit to emulating our perturbed parameter ensemble with an ensemble of neural nets rather than just a single neural network. First of all, this enables us to characterize the error. It also improves the accuracy and smoothness. And I can kind of show you this in kind of an example, a simplified example setup. So for a fixed set of microphysics parameters, we're going to evaluate one metric as a function of the background aerosol via running that set of parameters through the LES using a single neural network and then using an ensemble of neural networks. So here we have on the x-axis our background aerosol mixing ratio. On the y-axis, we have a metric. Here it's normalized liquid water path. So 0 to 1 is kind of spanning the full range of liquid water paths, average liquid water paths outputted by our perturbed parameter ensemble. The pink points are showing the LES outputs for a given parameter set. And then we can look at different neural networks. So this is a single neural network. For the same parameters that we put into the LES, how does it estimate this output metric as a function of background aerosol mixing ratio? And we can kind of generate many of these neural networks. So we can kind of see that the neural networks can capture the trend, but clearly there's some kind of mismatch. And in order to kind of better characterize this mismatch, we can kind of repeat this process of fitting neural networks to our perturbed parameter ensemble and generate a whole bunch of different neural networks. And we can see that by repeating this training process many times, we can get a fairly good coverage of the behavior of this property. And also we can estimate its uncertainty. And so turning this just 100 different values into what we would actually use. So here's the ensemble mean, and then I've shaded 1 plus or minus 1 standard deviation and 2 standard deviations. And first, we can see this is much smoother than any of those individual outputs, and we can also capture uncertainty of our prediction. And so one thing that would be great to discuss is there's kind of a number of reasons why we expect kind of the behavior of this kind of single slice of the data to kind of be general to emulating atmospheric model PPEs. And that's because kind of relative to other machine learning applications, we have a relatively low number of samples, a high dimensionality, and also we can have significant nonlinearity. And all of this makes the emulation process kind of uncertain, and we want to be able to characterize how uncertain our predictions are. And so next I'll look at some evaluation of this ensemble neural network emulator approach with leave one out validation. So basically what this means is we train 500 different emulators. So that 500 number is coming from the number of PPE members we started with. And then for each member of the PPE, we train an emulator that does not include that PPE member for training and validation. So then we can evaluate the performance of that emulator on that excluded PPE member. And then we repeat this for all of the members of the PPE so we can kind of characterize the performance of the emulator. So here I'm showing on the x-axis the normalized emulated output, and on the y-axis the normalized LES output for all 12 outputs that we consider and all PPE members. The one-to-one line is shown in this dashed black line, and we can see that, and each output is shown as a single point, and we have error bars based on the standard deviation outputted from our ensemble emulator. We can see that the points generally follow this line, and I've shaded these differently based on whether the points are coming from our Latin hypercube sampling or our single column model sampling that we use to generate the PPE, because that kind of is affecting how successful or accurate the emulation is. So here I've basically taken all of those error bars from the previous slide and collected them into a histogram. And we can see that the emulated uncertainty PDF is significantly different between the Latin hypercube samples and the single column model samples, even though we have more Latin hypercube samples than single column model samples in our PPE. And this is kind of demonstrating that our emulator performance depends on the distribution of parameters and the distribution of outputs we're trying to emulate, not just on the number of samples that we're taking. And we can also look at this in more detail by focusing in on specific emulated outputs. So here we're looking at surface rain rate, which is maybe one of the most, at least physically, one of the most important outputs that we would care about. And we can see that this is an output that's not being emulated super well, and we have very large uncertainty. So remember that 0 to 1 is spanning the entire range of the PPE. And so most of these Latin hypercube points, we basically are spanning the entire range of the PPE for our predicted emulation. And what seems to be causing this poor performance is if we look at the distribution of outputs that are coming from our PPE that we're using to train the emulator, basically all of them have a single value. And so we don't really have a lot of strong dependence on this output as a function of parameters, and that makes it hard for the emulation to work. So this is definitely something we want to consider moving forward as we're developing different emulation approaches. To contrast that, here we can see the cloud-based rain rate, which has, here we can see the histogram of outputs is basically pretty uniform. And this is, if we kind of compare the performance of this one-to-one line, we can see that we're doing a lot better job. Okay. We can also look at how good of a job is the emulator error prediction doing. And so what we find for kind of spanning both those Latin hypercube samples and the single column model samples, our emulator error is approximately normally distributed. So here we're going to show a distribution of the error of the emulator versus the LES normalized by the emulated uncertainty. And so we can see that this is kind of a unimodal distribution centered on 0. And I can add in what does a normal distribution look like. And there's some error bar on that because we are taking, we're taking a finite number of samples. And we can see that this isn't a perfect normal distribution, but it's fairly close, which kind of suggests to us that the emulator error is doing a fairly reasonable job at kind of characterizing the uncertainty of the emulator's estimation. And then finally, just I'll show a quick, some quick results, just kind of demonstrating that the Markov chain Monte Carlo estimation component of this procedure is working. So the test here is to use as a constraint the LES with the parameterization we're trying to fit parameters for used as a constraint. So we kind of know what the real parameters that we put into the LES are. And then we try to recover them via this emulation framework. And these are just showing corner plots for all 11 parameters that we're trying to recover. The pink line is showing the parameter values put into the LES, and these black curves are showing the marginalized PDFs that we're recovering, and you can kind of see that we're capturing these true parameter values in our estimate. And the exact width of these, or how narrowly we can constrain the parameters, is a strong function of what kind of metrics we use to provide the constraint, as well as like how many. So we can potentially narrow down or inflate how much of a constraint we put onto the parameters based on what kind of metrics we use to characterize the performance of the atmospheric model. And with that, I'll wrap up. And so just to kind of take some concluding points, we see significant benefit to emulating perturbed parameter ensemble results with a neural network ensemble versus a single neural network. This lets us characterize error and also improves accuracy and smoothness. We see that the emulation of the PPE depends not only on the number of PPE samples or the number of samples per parameter, but also on the distribution of parameters and the distribution of outputs we're trying to emulate. And then finally, I'll just say that, that this machine learning-enabled Bayesian parameter estimation via PPEs is appears to be a viable methodology for quantitative atmospheric model parameter selection. And with that, I guess I'll throw up some discussion questions, and looking forward to hearing your questions and the ensuing discussion. Thanks.
Thank you very much, Kaitlyn. It'd be nice if some other people could turn their screens on as well, so we can have what feels more like a discussion rather than a one-way chat. But to begin with, Greg has his hand up, so let's let you jump in, Greg.
I was actually clapping, but but I can also ask a question. Yeah, thanks. So Kate, can you I think I missed something about you were saying the uncertainties from the parameterization, which seem to be independent of the emulation step. Can you help me understand that again? How are you defining uncertainties from the parameterization? Was that by comparing to that single column model? Oh, you're on mute.
Where did I mention that?
Right in the very first or second slide.
Oh, okay. I don't know if, oh wait, here, I can just go on the bottom. Like this picture?
Yeah, so I understand key metrics and uncertainties from constraints, but then I was like, right there in the PPE. So I understand from the emulator and from the constraint, but I was like, well, what does that mean, uncertainties? Is that another thing you're explicitly computing from the atmospheric model and parameterization?
Yeah, so this is something that wasn't in, we haven't actually done this yet, but this would be like different dynamical realizations. So if we kind of change, you know, the seed of the random number generator that's initializing the LES, like what uncertainty in our parameter, or sorry, in our metrics does that produce? So we would probably expect that to be fairly small in these kind of domain and time averaged metrics that we're using here. But for example, if you were using like individual like grid point values, that noise might be quite substantial.
I see. Okay, thank you.
I think we should probably have your questions, Salua. Would you mind if we had your second question first and it linked to Yao Sheng's?
Yes, sure. I think I didn't understand completely what was your single column model sampling and how the minimum and maximum values are different between the two samplings.
Oh, yeah, sorry, that was just that figure was just like kind of a schematic. The minimum and maximum values are the same in for both sampling metrics. I also realize I mislabeled the colors here, sorry. But basically the idea is that we have some parameter space that we're kind of considering, and our constraints from a simpler model have more kind of clustered parameters relative to the range of possible parameters we explore in the Latin hypercube sampling. And the single column model constraint is just coming from, if I kind of go back to this initial picture, basically it's using, as the atmospheric model, a single column model, the same kind of parameterization setup, focusing on the microphysics. And as a constraint, we're using that same single column model with just a more complicated microphysics scheme.
So if I understood, the sampling you have at the end is because you already tested the SCM with different parameter values, and you selected you constrained with the performance metric to select the parameter values, right? Or
yes, so those
one first wave, right, with the single column model.
Yeah, so that's kind of coming out of using it's just kind of, we're just kind of looking for a way to get kind of more density of points than just the Latin hypercube.
Okay.
It's just to like get the LES to do something reasonable. So like a lot of the Latin hypercube points make like the entire cloud layer collapse or kind of extreme behaviors, and that sampling was just kind of a guide from a simpler model of where might be better parameters.
Yeah, okay, thank you.
If that makes sense.
Yeah, I think, yeah.
That also links to Yao Sheng's question. Yao Sheng, do you want to ask it out loud or shall I ask for you?
Yes, I can ask it. Hi, nice talk. I'm just curious how the two sampling methods differ so that the precipitation distribution from the single column model sampling is very nicely pre-uniform distribution across all the values you want.
So one of the I guess methodological points that I didn't really mention here is, which I think is also an important component of the emulation, is how do you kind of scale and normalize the data from physical units into what you want to use in a neural network. And there's certain basically this has been intentionally rescaled to be uniform. It's not actually the raw results of the PPE are more spread out. So another test you can kind of add to this is how does just scaling the data differently from kind of physical units into what you try to emulate affect the performance, and that's also kind of non-trivial. But the difference between this and this rescaling is that basically there's just a large number of outputs that are the same exact value in this case. And so no matter what kind of normalization or rescaling we do, like that's always going to give the same value if we rescale it. And so that's kind of the differentiating factor here.
Sorry if I missed it, Kaitlyn, but can you explain why that happens? That you get different parameter values but still get the same model output? Because that surely must have
Yes.
a big influence on your ability to predict.
Yeah.
those
So
parameters.
So this is also like one of the consequences of these kind of simple metrics that we're just starting with, as like, even if we just do kind of the crudest thing possible, what can we recover? Just a lot of, basically, given the dynamical forcing and the range of aerosol values that we're sampling, a lot of these conditions just don't generate any surface rain. And so that's why this zero is actually a true zero. It's basically just not raining at the surface. All of the rainwater evaporates before it gets up or down.
Did you consider what might happen if you remove those points from your analysis? So that you maybe had something that only was predicting rainfall when it's raining?
Yeah, so one option would be to kind of curate what samples from the PPE we want to put into the emulator, or we could potentially train a kind of classifier of like, is it raining or is it not? But I think either way, without kind of having a sample where we have a significant fraction of points in the non-zero regime, any emulator is going to have a hard time. Basically, you just have fewer points to kind of put constraints on the kind of setup of your neural network. And so I think definitely thinking about how to design your PPE structure so that it will give you kind of a range of different outcomes that you're interested in, instead of just like no rain.
That's it. It is an issue that came up in our workshop, and it's one of the points of consideration, isn't it? How do you design a PPE really well, gives you output of interest when you have to discard so many training points, but you certainly have some dichotomy in terms of model performance. So some sort of strategy in place in advance to say categorize those in that particular way a priori before using the resources potentially. Yeah, so a multi-stage creation of your PPE like you've described here, but maybe with more stages could be required.
Yeah,
that's probably straying into discussion because it's a deep question. Graham has a question which he may have put in the chat. Yeah, go for it, Graham. Yeah, I'm not sure if we can hear you, Graham. So if you could put it in either the Etherpad or into the chat here, then we can answer it. But there's plenty in the Etherpad for you to come back to, Kaitlyn.
Okay.
Oh, there he is. Go for it.
Excuse me, everybody. I'm technically challenged this morning, iPhones and iPads and things like that. Kaitlyn, I really enjoyed this. Unfortunately, I missed some of it, and so my question's probably naive. To what extent, I missed exactly what initial parameters you're perturbing. Are these parameterizations of the precip formation? Are these or are these aerosol inputs? Are these initial conditions, for example, in the form of your initial meteorology? So I know that you probably covered all of this, so excuse me for that question, but it helps me understand the sensitivity of outputs to your PPE. And could you just clarify that for me?
Yeah, for sure. So let me just go back. Yeah, so basically this is kind of a first step. So we're only considering kind of one dynamical forcing or one meteorological kind of setup of kind of drizzling stratocumulus. And then but that's something we're going to expand upon moving forward to have different kind of meteorological forcings. And then in terms of the actual parameters, so we have 11 microphysics parameters. Right now, we're only varying parameters associated with collision coalescence, and this is all kind of warm warm rain or warm drops. So we have a limited number of processes as well. And then we also are varying the background aerosol number in our PPE so that we can emulate the outputs as a function of aerosol.
Okay, good. So are you then using a bulk microphysical scheme with which gives you the 11 parameters? I suppose that might be something like Kruithof-Kogan, which already gives you about 6 or 7, I think, plus the aerosol. Is that, have I got that approximately right?
Yeah, so we're working with the kind of BOSS framework with that, but basically it's just a bunch of power laws and sums of power laws.
Okay.
So fairly similar to KK.
Okay.
But that's something we're looking to test, since basically also evaluate structural, the performance of structural change, the impact of structural changes on model performance as well moving forward.
Good. Okay. Thank you for that perspective, and sorry for the naive question.
No.
Looks like there's no more questions. So I'm going to come in with the last one, Kaitlyn, which was just if you could go back to your last image slide where you're showing the different 2D figures.
Oh, yeah.
And thank you. I got the impression this is like where these horizontal lines cross over is like the median in that 2-dimensional subspace. And then
So
the median
go
from
ahead.
1D subspaces, I guess, and then you've got a shaded section, which is the density of those 2 parameter values in combination. Is that right?
So sorry, I kind of skimmed over this. Basically, the crosshairs here are showing the actual parameter values that were inputted into the LES, and the edge, like this single line, is showing the marginalized PDF of each parameter. So the range of possible given the constraint, this is across all of, ignoring what all of the other parameters are. If we just cast this into a single dimensional space, say this parameter has a distribution to recover those constraints that looks something like this. And the shaded panels are showing 2D PDFs of the parameter space of 2 different parameter combinations. So for example, we can kind of see that some of these parameters are heavily dependent on each other, like this one or this one.
I think it's an excellent example of one of the key strategic priorities for the community, which is how we tackle model equifinality. Because it's really clear, isn't it, that there's no single combination of parameters that matches your criteria in any way much better than any other combination within this subset.
Yeah, that's definitely something that we're interested in, especially the difference between, I guess, when Marcus and Greg did this with the GCM, there's a lot of kind of global observables that we can use as constraints, and you're kind of limited by what kind of observations are available. But for the LES perspective, we can kind of design outputs from the model to use as constraints. And so depending what kind of metrics we pull out as constraints, we can get tighter or broader sets of good parameters. And so these kind of basic averages are giving us fairly broad constraints.
Yeah,
so we have a lot of equifinality.
You could always tighten it up, couldn't you? By having a tighter constraint that brings you down to just one combination of model parameters. But then obviously you have to test that in different conditions and see how it performs. So effectively saying you should broaden your basket of constraints first, rather than just make those few constraints tighter. but
Mhm, mhm.
I think there's sufficient literature out there to say what the best strategy for that is. It's an open area of discussion, isn't it?
Yeah. Yeah, definitely something we're interested in, and a big scientific question of this work.
So we've covered most of the questions that people had asked. There's a number of points that have been raised in the Etherpad that you can go and add to, Kaitlyn. I think you should possibly, if you stop sharing, and we can all turn our cameras on and enter into the discussion phase of this meeting. But I would mention that we only have 22 participants rather than the 170 we sent our email to. So it's possible not everyone had time to put it into their calendar. So the discussion may be shorter than anticipated today. Did you have your hand up there, Greg? Did you have something to add?
I was going to ask a follow-on to your question, but that's okay. Actually, you know, it might even be beneficial, Leighton, if because Kaitlyn didn't mention it yet, but right before everyone hopped on, she's actually going to rerun a PPE here within days, and she came up with those discussion questions. It might even be worth it to share those while we're as part of the discussion, since she had listed her own thoughts for discussion questions, unless that was just an option.
I'm on board with that idea, because there's, like I say, only 20 or so of us here. So
yeah,
we should draw on what expertise there is and contribute to that meaningfully. That sounds good. Unless anyone in the group that's here has something in particular they want to discuss, we could then carve up that time appropriately. So if that's the case, you should pop that in the Etherpad. Otherwise, we can make a start. So, Kate, do you want to share that again? That particular page?
Yeah, definitely we don't need to discuss this. I was just throwing out. Okay. Is that sharing or no?
Yeah.
Okay, great.
Yeah, so I guess we're really thinking about PPE sample, how to select the sample.
Yeah, I was just looking at someone on the sorry, I don't know what the name of that external link note is, but was asking about the ratio of samples per parameters being quite high. And I think that kind of is, yeah, I think that's a good question. I've been hearing a lot that there's kind of conventional wisdom on number of parameters, setting kind of number of samples you need. But what we're seeing in terms of the emulation, at least here, is that how those samples are distributed across your parameter space, or how broad it is, and what kind of range of outputs are you getting, might kind of you might need to have higher density of sampling.
I think that might be an issue that's particularly related to single column models and LEMs, because there's so many of the simulations that don't produce the sort of output you're anticipating, and you do get these bifurcations in model behavior. Is that a fair point or a fair perspective? I'm finding it hard to disseminate that from the fact that you've used neural nets rather than Gaussian process emulators, because the Gaussian process emulator forces the fits to go right through the training points in most conditions, whereas yours, you're satisfied if the training point is within a couple of standard deviations of the emulator uncertainty. It's a very different mindset in terms of the approach to training the system.
Yeah, we've also tried to really not overfit. So we could get a better fit for the evaluation points, but it probably would not be as kind of generalized, if that makes sense.
Yeah, I wonder how much that relates to the number of points you need, though, which is what we're discussing here, right? And what those points are. I think Jill might have something to contribute there.
Yeah, I was just wanting to say that it depends on what sort of emulator you build, maybe, as to how many points you need. So a lot of the work that Leighton and I and our group does has been with a Gaussian process structure, and with that it's got kind of inverting of high dimensional matrices, if you've got too many points, that matrix just isn't going to invert and you'll get mathematical issues with that. So whereas maybe within the neural network, it's something that I've never done is fit a neural network, so I'm quite interested in actually how it actually does it. But maybe that's something that you don't have issues with, so you can have more points, and more points the better. Whereas for the general, just basic Gaussian process, the more points the better is not necessarily the case in terms of training data over a space. Just thought we'd say that.
That's really helpful context. Thank you.
It's a discussion session now, Greg. You can help me co-lead if you like. So.
Yeah, we haven't quite I guess worked out on when to raise hand and when to just start talking. But anyway, so how do you like, if there's lots of zeros? So I guess the issue, right, is when you're like trying to come up with sampling is you have so many zeros sometimes, and then otherwise then and then you have this other set that like has some distribution. But you don't want to remove all the zeros, right? Like, how do you know? What is the general guidance for what to retain in training and what not for samples? Does anyone have any? Is it just like rules of thumb, or are there good does it all depend on what type of emulator you're fitting to the data? I guess that it depends on that too. I'm just very curious on thinking about it's scary to have to remove things, I guess is what remove training points. It feels weird, I guess. That's all. I'm just, because I hate to remove points.
Yeah, I think that's a good question, Greg. One thing that I have been seeing is it might not be that you need to have a complete a huge have every point be like raining or drizzling at the surface, or not be zero, but you kind of need a sufficient number so that you can kind of do a good job of emulating those parameter combinations, because otherwise there's just not sensitivity to, if every parameter gives the same output, there's no sensitivity to the output to the parameters. So I wonder if just getting enough, but it doesn't necessarily need to be balanced, is possible. I agree, like removing things seems, because you've lost information and you didn't have that much to start.
Yeah, it's just I don't know how one even knows in advance when you have enough. I guess that's part of my question too.
I had a bit of experience with this recently with one of my PPEs. So quite a lot of our simulations ended up not producing the stratocumulus cloud that we were looking for. So we had to remove quite a lot of points from our parameter space. So initially we kind of started with the recommended number of simulations per parameter this was for Gaussian process emulation. So I ended up just removing them because they didn't really have many other options. And it did actually emulate okay. And it was kind of hard to say, like, I guess I don't really know at what point is it, viable and what point is it not, because you look at it and it emulates and the uncertainty looks okay. So we kind of just went with it. But we also tried to kind of resample in areas that we knew that it would produce stratocumulus, just to try and bulk up the training data set a little bit. But yeah, I think it wasn't really something we came back to getting an answer on, because then we were emulating over this parameter space where there were sort of corners of parameter space where we didn't have any training data. And yeah, again, kind of just went with it, and the emulator looked all right, but we didn't really land on a kind of firm way to deal with that. And maybe we could have sort of chopped the parameter space up a little bit. I mean, in that case, I think it was sort of corners and edges that maybe could have been removed to improve that emulation. Whereas sometimes, you know, if you're just removing points, you're going to have holes in the middle of parameter space, and that's a bit harder to kind of chop and change with, I guess.
Mm-hmm. Yeah, I think one of the things I was also worried about then, because in the inversion step, like the MCMC step, when you're trying to, you know, so if you're removing what would look like a bad part of the state space, or, you know, because you're like, well, look, this is not, our emulator cannot handle this part of the state space. But then, you know, then when you fit the emulator, and then, you know, how do you then guarantee that during the MCMC step, it doesn't just accidentally point you back to that space because it doesn't know what's going on there, and it says, oh, these are good parameter combinations that you would want to check. And you're like, no, I wanted to avoid that. Like, I think my concern is almost in the parameter estimation stage after that you would be using the emulator as a surrogate model for. How do, you know, if you remove all those points, how does the MCMC know to not go back there and say, yeah, it could be good? I think that's my other kind of concern about you know, about how many things and how many parts of the state space to remove. But maybe there's just no good way to just, there's no good series of bullets or rules to follow for this, and it's all just, you know, just keep testing until someone comes up with something robust that applies to a lot of data sets.
I'm not sure how it applies to neural nets, but Jill and I in our work had a multi-stage PPE using a history matching approach. So we ruled out some parts of parameter space that just didn't match well to some observations, and then subsampled from the remaining constrained emulator space and made sure that we had a really big multi-million member sample that would suit all of the needs we thought we might have for that parameter space in the future. You know, we were being very cautious by having many millions, but that's only just designing where the parameter points would be and what the output from our emulator was. And then we created new emulators around that retained space. But I'm not sure how possible that is when you're having the MCMC approach, because it would expect space to be consistent, wouldn't it? Rather than avoid those.
Yeah, that's right. That's what I was basically wondering about. Yeah. Graham has a question. Graham, if you can unmute if you can.
Yes, I think hopefully you can hear me. So my perspective in this comes from the work that our group has done, which has looked more at the initial conditions. So these would be perturbed initial condition ensembles. And there you run into exactly the same thing. There are many combinations of your initial conditions, which might be things like initial temperature, vapor profiles, jumps, and this would be most appropriate for stratocumulus clouds, boundary layer depth, things like that. And there are many combinations of those that you can immediately exclude because they don't give you a cloud, or they give you a cloud that rains like crazy in the first couple minutes, or, you know, things of that kind. And here I think that it's actually this is your friend because it's basically limiting you know, the kinds of conditions you really need to deal with. What it can do, and Yao Sheng can speak to this as well, is that you do start to find some kind of covariability that you had hoped didn't exist in your Latin hypercube sampling. You know, you end up finding that there are certain conditions that with correlated initial conditions that tend to give you clouds. But again, I think this is meaningful because nature presents certain conditions that give us clouds. And so, yeah, that's just a perspective from varying initial conditions as opposed to varying parameters. But I do suspect that there may be some commonality here because, you know, if we're thinking of a microphysics parameterization, should we expect, and I'll just use KK as an example because it's easy to wrap one's mind around, should one really expect very strong dependence of autoconversion on aerosol or drop concentration as well as liquid water content? You know, I'm sort of making this up, but you know, what one could physically, I think, and this expert opinion probably comes in here, as well as bin microphysics models with the best kernels we know, as well as perhaps super droplet methods, where I think we could start excluding certain parameters and saying, you know, we don't need to worry about the combinations.
If I can chime in for a bit, again, I don't have a good solution, but just offering past experience with this as well. So when I was doing PPE work previously, I did something similar to what Leighton mentioned, is run like a reiterative process to generate different PPEs and then use emulators to repopulate that reduced space again very densely, then select a subset of PPE to run through an actual model again to see what the results look like. And I ended up having to reject of parameter combination as well, because they gave me really out of whack top of atmosphere energy balance. And I keep thinking, if they are so out of whack, what's the point of even keeping that space? So I can reduce that space by cutting out that multi-dimensional space to start with, feeding into the following steps of generating new PPEs. So I think, to me, the question comes down to, do we want to end up having a PPE that's more physically constrained and more realistic? I guess in terms of answering the question of throwing out points or not. So yeah.
Thanks, Jan. I think it's a crucial question, isn't it? Whether you discard some points and have a PPE that matches some criteria really well and then can perform at an expected level of skill, or if you have a PPE that's designed to work generally. But I think then you may need many, many more points to be able to represent the rapid transition from one regime to another. Can anyone speak to that?
That's interesting. So if you know where all of the zeros, like where it bifurcates, and then you know where things, then you have a new mode, almost like arguing that your sampling should really be increased in that where that break occurs, to see if you can fill out like a continuous state space.
I guess that would be one way to do it, wouldn't it? But you sort of need to know what the response surface is like before creating the PPE members. So you've got a chicken egg scenario, requires some iteration and augmentation of an existing PPE to get to that level, which is relatively straightforward in GP emulation. I guess that's tricky with neural networks.
Yeah, I would expect so. Go ahead, Graham.
So Jill can speak to this. The bifurcations become quite tricky, and the way that we handled this in our initial perturbed initial condition ensembles was to track these systems as a function of time, rather than just looking at input and then the final output conditions. And that way you can follow these systems as they pass through those bifurcations, and you can fill in the space that way. And Jill and others, well, I guess this was Pope et al., did a whole paper on bifurcations and the difficulty of handling bifurcations. I'll let Jill speak to that, though.
Yeah, so we did in Chris Pope's work, we did look at using Voronoi tessellations to define areas of parameter space that were in different regimes, essentially. So if you can define where your areas of parameter space are in those different regimes, then we did some retrospective sampling. We resampled and did a few extra runs around where we thought the edges of this were, and we got some nice results with that. So there are methods out there that would do emulation, at least with a GP, from a GP rather than neural network perspective, that would do that. I did want to sort of ask a question. This is probably a really stupid question, and I'm happy to accept it is, but is there a difference? You know, we're talking about taking points out, and I think there's probably quite a big difference in running an ensemble, deciding it doesn't work as an error, and just taking that data out and not using it, and putting constraints on your parameter space and deciding before you make your ensemble where you don't want to sample. Because when you just take data out, you're taking data out in all 6 dimensions. You know, if you've done a space filling design over all 6 dimensions, your space filling is no longer all over 6 dimensions. When you start to take it out because of 2 points, you're actually taking it out across all the extra dimensions that are in there. So I think you lose a lot more information when you do a PP and take data out and then just don't use it, than if you work out which bits of parameter space, like Graham was saying, which bits of parameter space we know that's not going to give us a cloud, let's not sample there at all, and have some kind of way of defining what that constrained space is before you sample it. I think can be quite a difference in what you might get. I don't have no proof of that, so I'm happy to someone to argue against that, but I think that can be 2 quite different situations.
I was kind of thinking in 2 different ways. So if I understood Graham correctly, it seemed like there is a value in retaining those points, so you don't get a cloud, and you want to know what were the situations where that didn't happen. That seems of use. But then I was distinguishing between that value versus that problem that arises when trying to fit in emulators to the whole thing. So I feel like it's almost like 2 things, right? It's sort of like that is interesting to know where that happens, but then it poses a problem in trying to fit an emulator to the whole state space. And you know, so it's almost like I don't know. I guess you'd have to, you know, if that problem is worth not sampling, or it makes it reasonable to not sample that state space. But in my mind, I feel like these are just still 2 separate things. One's about fitting an emulator. One's about knowledge of where that occurs. So you don't want to have those points, or you have knowledge of those atmospheres that cause that issue.
Yeah, I agree that it could be 2 steps. I'm more familiar with neural networks than Gaussian process, but just like Kate said during the talk, many problems can be separated into first training a classifier and then training a predictor, or first training a predictor and then a classifier. So I don't think we have to discard. I mean, depends on the nature of problems. We don't necessarily need to discard data. If we can create a classifier, say, okay, we just mask off some area of parameter space, that's good enough, right? Especially if this makes fitting the whole data sets, even some of the data points are not reasonable, fitting to this whole data set is easier, then divided into 2 steps is a very viable approach, I think.
Someone's doing what I just did, typing with the mute off. Sorry, everyone. I think it's really interesting, but it then does automatically feed into a need to increase the number of ensemble members, right? If you're training a classifier, then a predictor. Like in Rachel's case, the situation Rachel described, she had no choice and couldn't use those members because they didn't produce cloud of the type she needed to come up with a metric to define to create an emulator. So those model runs had to be discarded. But in the way Kate's done things, you've got an opportunity here because you have a neural net that fits the entirety of the data, and you could make another neural net that fits that subset that doesn't include zeros and see how that performs. Even though there'll be many fewer members in there.
Yeah, and I think Kate's actually about to I mean, if I understood correctly, Kate, I think you're about to resample too, right? You're about to rerun everything from scratch. So you could even test this idea of sampling, you know, heavily. I think there was a notion that like a few thought 500 samples was a lot for the number of parameters you were perturbing. But I wonder if you could just do the same number for your next round and figure out where that sharp break is, and sample and devote a lot of your new sampling into that region to test some of these ideas. I mean, if you have that computing, if you have those resources and you're just able to play around and you know, I don't know what your setup is going to be, but I do think you did say you're going to resample.
Yeah, I think with the neural networks, as long as there's, which this is the metric, I don't know how you evaluate, but as long as there's there are enough points that do have, like your outputs have some kind of gradient. So even if you have a bunch of zeros, as long as you have enough points that aren't zero as well, you should be able to map to both spaces. But I think the challenge is how much is enough outside of that. And maybe I'll think about, I was just writing down to like maybe train a classifier and maybe sample more heavily from, say, the reigning space, which is, we don't have a ton of samples from currently. Yeah, it's a good idea.
So before Salua jumps in, I'm going to say that it is a high ratio compared to our Gaussian process PPEs, where we're currently at the climate scale and regional scale getting away with 6 runs per parameter compared to over 40. So big difference. Yeah. Sorry, Salua.
No, yeah, I think it comes back to some things we already discussed, but right now you don't, if I understood, you don't really know how many parameters are responsible for this state where you don't have the clouds. So you can imagine having a predictor of whether you have the cloud classifier, it's a classifier where you have them or not, and then do a sensitivity analysis. And maybe you end up having just 1 or 2 parameters to truncate, like to, yeah. We talked about that, but I think, yeah.
Yeah, I agree. I think one of the drivers might be that the parameter space is really broad, and probably, I suspect, only a few parameters are kind of driving a lot of the cloud collapsing effects.
Maybe.
One of the things we try and avoid in the Gaussian process PPEs is having points that are too close together, because then they can affect the quality of the fit. I wonder what's the effect with your single column model in having so many model parameter combinations so close together? Do you have much of a sense of how that affects the neural net?
Yeah, I think it is a big help. Like, I think you could kind of see a distinct performance of the points when you exclude the points from the PPE that were from that more densely sampled region. They perform a lot better. The error is a lot tighter. Whereas the broader Latin hypercube sampling, kind of, when you remove that point, you're kind of out to lunch. So yeah, that kind of methodological difference, it seems like, is kind of something that I will look more into. That seems quite.
What's that suggest to you then? Does that suggest you need more points in the Latin hypercube part of your design to get better spatial coverage and therefore more information? So that fewer points are at the lunch?
That seemed opposite of what you were first saying, Leighton, right? It seems like it sounds like Kate saying, no, more dense is better, or closer points are better.
Yeah, but she's got that space covered, right?
Yeah.
Like that central space is behaving in a way that's understandable and predictable. So to get something that expands from that to be better in the rest of the space, I'm just wondering if you're going to commit more resource to one or the other, where you're thinking to do that.
Yeah, I think, balancing being able to cover like unanticipated parameter combinations versus getting better emulation. So like right now, I think a lot of the Latin hypercube region, we probably couldn't get really great constraints on the parameters there. They'd be like very inflated because the error is so large. But the main approach I was planning to take previously, which I might reevaluate, is trying to shrink the bounds of the Latin hypercube space. to make it more dense naturally.
The other sort of kind of diverting the topic a bit about how to design the parameter space. I had a question that I wanted to ask about the ensemble of neural nets that you mentioned, Kate. I think I didn't quite understand that part. What do you mean by an ensemble of neural nets?
Yeah, that's a good question. I definitely I cut those slides. But the idea is basically that there are a bunch of choice of kind of design choices when you're training a neural network. So how many layers are you going to have? How many nodes do you have in each layer? Certain like training parameters, and varying all of those will kind of affect the neural net your training process produces, as well as just kind of random initialization differences. And so here we construct the ensemble by just kind of varying the hyperparameters of how the networks are set up. And then we also vary, we subsample as the training versus validation data, our full data set. So network one might see, we'll see like 80% of points as training and 20% as validation. And then network two will see a different combination of training and validation. And so that lets us not overfit while still seeing the entire data space. And so that's how the ensemble is constructed right now. But there's a bunch of different options you can add to enhance that, or people just make network ensembles just varying like initialization and the same architecture and still see diverse networks generated. So
yeah, I guess based on my very primitive understanding of neural nets, each time you run the architecture or the algorithm, it generates something slightly different. So in the end, when you're validating or comparing the ones that are run with the light hypercube design versus the single column model design, so are you tracking which neural net architecture you're using for each of them when showing those plots? I'm not sure if I'm communicating what I want to ask clearly enough.
Yeah. So basically there's like a few stages. There's like a filter stage to choose network architectures. That's like something fixed. That's not that doesn't have any randomness to it. Which ones kind of perform well for the way the data is shaped. And then from those kind of well-performing kind of like fixed properties, then we can kind of train. And so you could in principle like make everything reproducible. This is something that needs to be added to the code by just setting all of the random, basically just like tracking all the seeds and making sure that the random number generator does the same thing every time. So there's randomness in how you kind of, the starting point of where you initialize the trainable parameters in your network. So that's one area of randomness. And the other area of randomness is potentially, depending on how you are doing the training, there might be some stochasticity in how the next step is taken. And so what we do is like save the model after that training has been done, and then everything is kind of frozen in place at that stage and then run, if that makes sense. And then for this difference between the Latin hypercube points and the single column model points, that's just in that scenario, we were just excluding a single point from the ensemble construction. So we made maybe like in total about like 500,000 different networks, and then they were put into ensembles based on a single point being excluded, if that makes sense. But everything was kind of, once the training is done, the model is kind of frozen. So that part isn't stochastic.
Okay, thank you.
Looks like we've reached the natural end. Thank you very much, Kate. You didn't expect to be hit with questions the entire time there, but that's a good way to facilitate our discussion. And we'll have to obviously plan how these discussion sessions work. So if you have any feedback, get in touch with any of the organizing committee and let us know how we do things. But I thought that was really rewarding, good conversation. The Etherpad's there as an ongoing record, so you can come back to that and be helpful, Kate, if you wanted to add in some detail at some time, maybe not today, it'll be there permanently. So sometime put in some answers to those questions. It gives you that opportunity. I feel like we could have dug a lot more into model equifinality and talked about the types of constraints you applied, but it's early days, right? You've still got more to consider in that regard. So no doubt we'll come back around to that priority, that community priority. We'll be in touch soon to let everyone know when the next session is, but I think we should thank Kate, those of us who've got our screens on and those who don't.
Thank you.
Thanks, Kate.
And thank you all for your feedback, super helpful, and yeah, definitely will help us move forward.
Thank you.
Thank you. Very interesting.
And thanks everyone for joining. That's great.